All right, let's get going. Today we have Raksha Kumaraswamy. She is a PhD student and she's going to tell us about stochastic optimism and exploration.
Hi everyone, thank you for tuning in. Uh, so for folks who read the abstract, I'm sorry, but it's going to be a little different. Hopefully it's just more useful for everybody and you're not too disappointed. So I'm going to be talking about the idea of Bayesian methods for model-free exploration with some focus on stochastic optimism. This is still a work in progress with Martha White. The key takeaway of the idea is that we are looking at Bayesian methods for learning value functions because we think it's an effective avenue for inducing online model-free exploratory behavior. But in this large umbrella of buzzwords, are there any methods that exist right now? Yeah, there are, which is this idea of RLSVI and Bootstrap DQL. Both of them are methods which have shown promising empirical results. But on the theoretical side, RLSVI in particular has been shown to have this promising theoretical guarantees with this key idea of stochastic optimism. So moving along, what we are thinking about is how important is the idea of stochastic optimism, or how exactly should we go about deriving effective online model-free exploration methods, Bayesian value functions. To sort of get started, I'm just going to present the problem setting very briefly. We're interested in the problem of online exploration. What do I mean by the setting? We have an agent, this is a very simple example, but we have an agent in this tiny grid world, and it starts in the bottom left corner of the domain. The domain is episodic in that it can terminate at a sack of gold or at a pot of gold. Because the sack of gold is easily accessible, a random policy might stumble upon the sack of gold first, but the better policy, the optimal policy, is terminating at the pot of gold. So we're interested in inducing exploratory behavior, which would look for a pot of gold scenario, even if the sack of gold policy sounds promising. And given this exploration framework, the objective of the agent is still to learn the optimal policy pi star, but taking into account the fact that this is an online framework as opposed to an offline framework. So the goal for online exploration is essentially to promote behavior that visits unseen parts of the MDP, promote behavior that visits uncertain parts of the MDP. I'm trying to differentiate between the two because if just because a part is seen as an experience once, it does not have to be learned about perfectly. And additionally, we would like to learn a policy pi star with as few samples as possible. This is a very broad topic, and there's a lot of work done in this regard already, but we're going to be focusing on it. Why not just maximize reward? That is true, but maximizing reward would just be a surrogate for what the optimal policy is. If you don't have like effective exploratory behavior, which can go explore the complete MDP, for instance.
I'm confused about what's surrogate for what. I said that the reward is the main goal and everything else is surrogate.
That's true. I mean, you could maximize reward by, in that really simple example, where you continuously go to the sack of gold, but actually you would be getting higher reward if the policy learned terminated at the pot of gold instead. So we are interested in maximizing reward, but not settling for suboptimal policy.
I think you're still interested in maximizing reward, but you want to take into account your uncertainty about the word.
It's true, yes.
Okay.
So uncertainty about the world is kind of wrapped into these two ideas of unseen parts of the MDP and uncertain parts of the MDP. And additionally learn the optimal policy with as few samples if possible. just some really brief RL details. We're going to be looking at value functions. So we're interested in learning value functions, the optimal value function. The optimal value function is the expected discounted cumulative reward into the future while following the policy, the optimal policy as dictated by the dynamics of the NDP, IP. Additionally, the current estimate of the optimal value function is denoted by QTSA, wherever it's used. But it's just an estimate. It's not equivalent to Q-pi status. We're looking at the model tree exploration setting, but just to provide an overview of what is the existing work out there with respect to exploration and linear function approximation. Many methods try to induce exploratory behavior by learning value estimates which are optimistic with respect to the optimal value estimates. So the hope is to derive a QT-SA at some point, which is greater than or equal to the actual Q-star SA, therefore inducing behavior which is exploratory. A very naive way of doing this is optimistic initialization. It's easy in a tabular framework, but it's hard to use effectively in a function approximation framework. Further, it's also confusing in an uncertain world, the amount of optimism that is necessary for inducing effective behavior. The second umbrella of methods are based on this idea of bonuses. So here, the motivation is from a work in tabular RL called model-based interval estimation, but the idea is to provide bonuses in technically new parts of the NDP to promote behavior, to go back to the new parts, thereby kind of expanding this area of what is known to the agent. But bonus-based optimism has had limited empirical success in the function approximation setting, and lacks theoretical realities in that framework, but it's been shown to be an effective strategy in the tabular RL setting. Many of the deep RL-based exploration methods have been bonus-based, but there's also recent work that talks about how the methods might have been optimized for the particular RE game, Monsuma's Revenge, as opposed to being a good exploration method in general. I can provide references in the end if anyone's interested. On the third set is uncertainty-based optimism. Uncertainty-based optimism methods are interested in the idea that Sava mentioned, which is essentially reducing uncertainty about the NDP. If the uncertainty estimates are comprehensive such that the optimal value function is within the set induced by the uncertainty estimates, then these methods are really promising, but many methods that try to promote exploration for uncertainty-based optimism are usually estimating uncertainty with respect to Q pi t, which is your current estimate, current value function, so current policy, as opposed to Q star, which is the optimal policy. So it's hard to obtain uncertainty estimates which are optimistic with respect to Q star. And that's the problem we're looking at. We do think uncertainty-based optimism is a promising strategy moving forward. Why do we think so? Some really high-level arguments. Such an approach should, in theory, if we were to have uncertainty which included Q star in the set, would promote behavior to visit unseen parts of the NDP, but would also be effective in the sense of it would only be visiting unseen parts of the NDP where hopefully it's useful to learn about because it is about the optimal policy. But additionally, it would be promoting behavior to visit uncertain parts of the NDP, which would be useful for learning about the optimal policy as opposed to useful for just minimizing uncertainty, which can also be a criteria, but it's not a criteria in the optimal policy learning. And given the first two settings, hopefully we would learn the optimal policy with as few samples as possible. Turns out these are quite hard to estimate, and many people have been trying to for a while. But a promising strategy. But while we think uncertainty-based optimism is a promising strategy, what we would like is uncertainty estimates with respect to Q star. A class of algorithms which do maintain uncertainty estimates with respect to, let's say, a function space is Bayesian methods. So what methods would maintain uncertainty of function spaces? Inherently Bayesian methods. So we're going to shift focus from looking at just learning a particular value function to looking at learning a distribution over value functions. So what's the idea behind Bayesian value functions? We have this idea of a prior over the value function space, where let's say your prior is uniform, but your set of value functions is large enough that it encloses the optimal value function. You get a batch of data which is fit with respect to this function space with value iteration like update, so least squares value iteration, which produces a posterior over the value function space. Now your density is spread out over the value function space such that the more promising value functions which fit the data are effectively have a little more density. You continue this loop for a while, and that's the broad idea, that this loop continues for a while, and hopefully at the end the posteriors converge such that the density is only distributed on the optimal set of value functions if there is more than one. Have these methods been shown to be effective? Theoretically, in the finite horizon setting for tabular RL, it's been shown to have a particular regret bound, which is nice and motivating. Additionally, empirically, they are effective up to an extent with the linear function approximation setting, and have also been shown to be effective in the deep RL setting. Why do I say up to an extent in the linear function approximation setting? Because I've worked with RLSVI a little bit, and while we evaluate it from the perspective of online policy, the quality of the online policy, it's not super great. There are other methods in linear function approximation which may do better, but from the deep RL setting, Bootstrap BQN is another algorithm which tries to do this idea of Bayesian value functions, and they have pretty good promising results. So in this regard, as we're interested in learning value functions, distributions over value functions that are effective, the key for RLSVI being effective is this motivation from a tabular RL setting, where the idea of stochastic optimism has been important to show that it's a useful approach. So we're just going to take a look at this idea of stochastic optimism. Take a closer look at the idea of stochastic optimism, which has been key for providing good theoretical guarantees for RLSVI in the tabular RL setting. RLSVI does not carry over this guarantee for the function approximation setting, and we're interested in the function approximation setting, so we've just been exploring what the ideas out there in terms of would be fruitful for incorporating in the function approximation setting. So given this, just to provide an overview of stochastic optimism quickly, it's a concept that's extensively used in the area of finance, economics, and game theory. People who are familiar with it, maybe it's also called second-order stochastic dominance. But stochastic optimism is defined by Osborne et al. In the RLSVI work. It provides a way to partially order random variables. So what does it mean to order random variables? I will provide examples in a bit, but essentially the idea is a random variable x is stochastically optimistic with respect to another random variable y if the area under the CDF of x is always lesser than the area under the CDF of y, valued at any point. So, and it's denoted by x is stochastic optimistic to y. Before I provide an example in terms of density, I'm going to provide a naive example first. Yeah.
I have a clarification. So the area under the curve you mean by from minus infinity to x, that's the area you're measuring?
Yep. Okay. For all x's that you evaluate.
Yep, okay.
So this is a little funny in the sense that CDFs are already area under the curve with respect to a PDF, but I'm just going to mention one motivating example for this, and I have examples of densities. We can look at them if we want to at the end of time. So let's say we have access to a gambling budget of 1,000, going back to a game theory perspective. We have two scenarios where both of them have the same probability distribution for over two outcomes. The first scenario has a 99.99% probability of getting 2,000 if you bet 1,000, and 0.01% probability of getting 0. Alternatively, the second scenario has a 99.99% probability of getting 0 and 0.01% probability of getting 998,000. So given this distribution, the expected values of these two scenarios are the same, but the distribution is so skewed in the scenario such that if you were to sample from scenario 1 with a few samples, you would be estimating the expected value more accurately than if you were to sample from scenario 2. And that is the entire idea of stochastic dominance. That is one form of the idea of stochastic dominance, where scenario 1 is said to be stochastically optimistic with respect to scenario 2 if just from a few samples the expected value is a closer estimate to the expected value. To put in terms of the CDF, this is a last minute diagram with respect to the CDF of these discrete distributions. Sorry. But if you were to look at the CDF of scenario 1 at the value 0, it's only at 0.01. Alternatively, at the value 0, the second scenario is already 99.99%. So if you were integrating the area of the curve at any point here, area under the curve, this would have lesser area with respect to that. Same idea extended to infinity at any point, the area under the curve would be lesser than scenario 2. Yeah.
Can I ask a clarification question?
Yeah.
So is it always true that if X stochastically dominates Y, then it will be easier to use samples from X to estimate the mean of Y?
Not to estimate the mean of Y, but to,
Okay.
it's not true in order to estimate the mean of Y, but it provides you with better, it provides you with a distribution which is stochastically optimistic with respect to the underlying distribution. It's not that the expected value is better, but it's also that samples from this distribution are more optimistic than samples from the other distribution.
Okay, which is different than what you said before. Okay, fine.
Yeah.
Okay.
But not for estimating the expected value for sure, because
Yeah.
you can have two completely different expected values.
Exactly. Good.
So the question is, how does stochastic optimism help in the Bayesian value functions framework? I have examples of stochastic optimism with respect to like Gaussian distributions if you want to look at it later, but now I'm just going to briefly provide an overview of how it's been shown to be useful in the tabular RL setting. Our hypothesis is that this idea of stochastic optimism helps us overcome the first hurdle with respect to online exploration, which is it would promote visitation to unseen parts of the MDP. So it's not promoting visitation to reduce uncertainty as much as just promoting trajectories which would go to the borders of the known MDP and therefore stumble upon more unknown regions. So we're looking at, with stochastic optimism, we're looking at this idea of QT-SA being stochastically optimistic with respect to Q*SA. But although I say Q*SA here, I should mention that Q* is not the optimal value function, but it's the optimal value function conditioned on the data you've seen. So I'm going to try and explain what I mean by that. The first bit of the framework is essentially Bayesian value function framework, where you have prior value functions, you get value data, you have posterior value function space. The second component utilized to show such stochastic optimism is, the QT-SA is a random variable where W is sampled from this posterior value functions, and therefore QT-SA is, as W is random, QT-SA is a random variable as a consequence. We have the second part of the utility is from this idea of having a prior over MDPs. This is motivated from tabular, like classical exploration methods in tabular RL in terms of model-based interval estimation and PSRL, where given a prior over possible MDPs, and again a batch of data, we can estimate a posterior over possible MDPs. So if our prior is comprehensive and optimistic enough to include the actual MDP, then this posterior would hopefully have higher density with respect to the real MDP the agent lives in. Given these posterior over MDPs, Q star SA is now the optimistic value estimate is the value estimate as given by this optimistic MDP. So W again is sample W, and yeah. So we sample an MDP from the posterior. We utilize least square value iteration to learn the value function for it, which corresponds to W. And now given this W, which is a random variable as consequence of the posterior being sampled, the MDP is being sampled from the posterior, Q star SA is a random variable, and the idea is that QTSA is, would be stochastically optimistic with respect to Q star SA. What do I put words to this? QTSA is the optimistic value estimate with respect to our Bayesian prior over value functions. Q star SA is the optimistic model estimate with respect to our prior over feasible MDPs. And the idea shows that the value functions learned by RLSVI are stochastically optimistic with respect to the value function that would have been learned with a model-based strategy. So this is trying to promote exploratory behavior in a model-free learning environment with guarantees that model-based algorithms will provide you. So that's essentially where the idea of stochastic optimism comes in. To just provide like a few concluding remarks about why we're looking at this. Empirically successful Bayesian methods have either not been shown to produce stochastically optimistic value estimates of the function in the approximation setting, or have not been evaluated, have only been evaluated in the offline RL setting. So not for the online performance evaluation, but more take the learned policy and estimate the accumulated reward of that learned policy. So we're looking at the idea of stochastic optimism as a method to induce effective uncertainty with respect to Q star in the online RL framework. So where we would like to learn the optimal policy and hopefully behave according to it. And additionally, this has been an effective strategy with tabular RL in a very limited setting. So is there any other particular works that would actually be effective in for giving what we want instead of this particular strategy? So that idea. To provide some references of what I was talking about. Thank you. If anyone has questions, I'd be happy to. Any pointers to empirically so Chava asked a question about any pointers to empirically successful Bayesian RL algorithms. I think Bootstrap DQN, but again, it's been evaluated only in the offline RL setting, not in the online RL setting.
Is that a Bayesian algorithm, Bootstrap DQN? It sounds like a bona fide frequentist approach to me, like bootstrapping is not Bayesian.
That's true. They're trying to, I think, in spirit, be Bayesian with respect to neural networks. So if you have a bunch of neural networks, and
so they somehow connected to the Bayesian reasoning, but. Yeah.
But
yeah, I still want to see any empirically successful Bayesian RL methods.
That's true. That's true. RLSVI, even in the cases where I have worked with it, which is linear function approximation, is empirically quite heavy. Sorry, computationally quite heavy and empirically quite limited compared to other linear function approximation methods like, don't want to be a plug, but UCLS. Additionally, but RLSVI has good rigor bounds with respect to a tabular RL finite horizon setting. instead of a regular function approximation setting.
Yeah, I mean, Thomson sampling, we can mention that, or posterior sampling, reinforcement learning in whatever settings, those are not really empirical successes, but more like theoretical advances, which may one day lead to some great empirical successes, hopefully, but...
Yeah. So
yeah.
we're looking at this idea from the perspective that we think function approximation and Bayesian like learning strategies are maybe amenable together because we have a fixed function space that we are hopefully trying to learn with respect to. And if we could, we currently have work which tries to do uncertainty estimation with respect to Q by T. So like that's like a policy iteration kind of strategy, very loosely. But
have you seen this paper, the OPPO, optimistic policy optimization with, I don't know, like the third, or what is that? I can provide a link. It's doing it. It's only finite horizon setting, linear MBPs, but you evaluate your policy in an optimistic manner, and then you basically run polytech. So you basically sum up all the previous optimistic functions, you put a Boltzmann distribution on it, and then that's your next policy. So you do this soft policy improvement thing, and it has provable regret bounds. It's kind of neat because it's model-free, and so it's relatively low cost. And you can imagine that on policy, optimistic policy evaluation is easier, much easier. And nowadays, guys are proving that that's even sufficient for efficient exploration, at least in the setting they looked at. Yeah.
It sounds a little like Polytech, but it sounds a little like Polytech in the sense.
Yeah, it's something like that, but they put optimism on the top of it. So
that would be great. Thank you.
Yep, optimistic proximal policy optimization. Okay. Well, Robin had a comment.
Yeah, I think it's a link to a follow-up work of Bootstrap BQM, which talks about randomized priors for learning with value functions, deep RL-based framework.
Okay.
They also have another work, which is this idea of uncertainty Bellman equation, which tries to do like a policy iteration based uncertainty instead of a value iteration based uncertainty. But again, the empirical successes have been.
So what are the empirically successful papers that do any sort of principled exploration or would be able to solve harder exploration problems? If you remove any other restriction on that. I think we do have a few examples which are kind of like getting there, but
I think one example is RLSA, which is like trying to get there in terms of theoretical and practical considerations.
Okay.
But
there is this Agent 57 paper. Have you heard about it? It's like 57 different shades of, I don't know, color. The 57th iteration, I think, of the agent. That's why Agent 57. But it's doing some interesting, it's putting some interesting tricks with around exploration. So it's like, I wouldn't call it like absolutely principled, but it has some reminiscence to principled algorithms.
Yeah, that sounds good. I will take a look.
Yeah. What else?
I think from looking at motivation from tabular RL, delayed Q learning was one idea.
Which Q-learning?
Delayed Q-learning.
Delayed. Oh, delayed Q-learning. Yeah, horribly inefficient. Forget it.
Yeah, to the extent it's the function
bad
approximation
idea. Really bad idea. But so if you're talking about tabular setting, that is guys who prove that you add little bonuses to Q-learning, and then you can make it regret rate optimal or whatnot. Like it's not missing much on the regret. It's a paper by 2 years ago. I think Sebastian Beback is on the paper. Some others. Yeah, which is I think a much better result than the delayed Q-learning result have been. But I think maybe that's relevant for your work because that's Q-star, right? Like they go directly for Q-learning, they add little bonuses, and at least in a tabular case, they show that that works.
Sorry, you mentioned Sebastian Beback 2 years ago?
Yeah. And I think maybe yeah, like Chi-Jin. Let me put the link here. Zayn, Alanshu, Sebastian Beback, Michael Jordan.
Hi, thanks for the talk. Can I ask, if you're in an online setting, is there situations in which optimism is not a good idea? Like, for example, if we had some kind of medical RL agent, we might not want to explore with optimism. But how would we characterize those situations?
I haven't really looked into that area much, but there is an active community in terms of safe exploration, which is exploration in a risk-averse manner. The works that I've been talking about are mostly in the spirit of optimism in the face of uncertainty. So it is, if you don't know something, you try it, you either learn something from it or helps you improve. It's a pretty find out kind of an idea. But I don't really know much about but I think it's involved around imposing constraints on the physical policy space to control this value iteration like updates to not lead to destructive or cost-intensive policies.
So there's been quite a bit of work by the group of Andreas Krause around this, and then I know that control people in EPF Zurich, Melanie Seilenberg, also looked at it from the control perspective, some extensions there, and a different line of research was pursued, but it's like similarly safety and exploration together by Mohamed Gawamzadeh and a bunch of other people. So Andreas Krause starts with assuming that you have a safe body sense, so you gradually, like under some smoothness assumptions, can extend the safe region that you're exploring. There are some interesting ideas there of how to do these extensions. And Mohamed Gawamzadeh, he's looking at a different way of formulating the problem, which was that you have a baseline policy and you don't want to lose much reward compared to the baseline. So there, safety just means that you're not losing much reward compared to a baseline. And so there the idea is, like the basic idea is not super complicated. It is just like you run your baseline policy for a while and you build up some buffer, exploration buffer, because you're allowed to lose like 10%, let's say. You have a little budget to lose, right? You can use that for exploration. So when you collected enough reward and you say that, oh, now I can lose a little, so let's do some exploration. And then you explore until the buffer is gone. And if the buffer is gone, you again start to build up the budget by switching back to the baseline policy, and you do this in a principled fashion. Eventually, you can drift away completely from the baseline policy, and you will just learn whatever is the best. But you kind of slow down the rate at which you're losing due to exploration, so that no one gets really nervous about that you're losing a lot, right? So these are very different scenarios, but yeah.
Thank you.
Yeah.
Do you have any comments on benchmarks for this type of optimism and uncertainty? Like I saw the deep sea experiment in B suites, or is there something better than that, or what, do you have any comments about benchmarks for that stuff?
In terms of domains, I mostly tend to look at smaller scale domains like tiny grid worlds or the classical problems of control in RL. I think one issue with maybe starting at the level of these wide benchmarks is it's hard to reason about why the behavior you're getting is what you're getting in terms of the function approximation framework, for instance. The work I've mentioned in DPRL in terms of bonus-based methods, they were all aiming for doing well with respect to this one particular benchmark, which is considered really hard in terms of exploration. So it can be a little disheartening maybe to start that way and then realize the benchmark is an extreme case example for effective exploratory behavior. So I haven't really looked at high-level benchmarks so much. I look at classical control problems. Yeah, the Saba has a comment in the chat. Yeah, RLSKI did use stochastic dominance in their proof to essentially, they split the regret they would experience to two terms. One is bound, one is a term which tells you how fast you would estimate these optimal values, and another is a bound that tells you how optimistic would you be with respect to the optimal values of the data you have seen. And they show that stochastic optimism helps you get rid of the second term. So now the regret is only controlled by the first term, called the delta concentration inequality. It's a little different from, I think, UCRL and UCRL2 based regret methods, but they do use it for showing effective tabular error.
I don't want to take the time up from everyone else, but I have so many other questions. So how optimistic do we want to be? Like, is there some way to think about how much optimism we should carry? Is that something that we can learn from the MDP? And maybe that comes back to my other question, like, if you didn't know, like it seems in these safety constraint-based RL stuff, you have to know going in that you need to think about safety and constraints. But if you're just given a new MDP, like a new Atari game that has never existed before, and you don't know, and you're learning online, and you don't know if, like in your maze example, there's actually a really nice pot of gold far in the maze, right? A really big one. But what if that was like a horrible death trap instead? Then your optimism will lead you to a big negative reward, your optimistic exploration. So there's some kind of line between MDPs that in which optimism is going to help you and MDPs in which optimism is going to hurt you, and we might not know going in. Well, I think a lot of the work already assumes that we know which side of the line we're on before we start.
Not really, because optimism in the face of uncertainty doesn't really guarantee improving policies of value estimates. It doesn't, or rather, it doesn't preclude experience that would be hurtful. So you don't really know which side of the line you fall on when you start off with a method like OFU, which is built on the principle of OFU. I don't think I know of methods which would be able to exploit this idea of which side of the optimism is my current estimate fall on, because it's a little hard to do in a limited function approximation setting possibly. But also, yeah, it's a little hard to do, but I'm just wondering if I know of any work that does use it.
I think that we don't even need functional approximation to see that this is a bit hard, right? So you could just have an MVP and maybe two states. You start in one state. Like, do you want to see the other state? Maybe it's heaven. Maybe it's hell. What are you going to do?
It's the pure spirit of optimism in the face of uncertainty is not scared.
Yeah, so these algorithms assume that there are no irreversible traps. So optimism kind of, like it works if you can recover from failures. If you have little failures, then you need some other background thing, because otherwise nothing is going to help you. So I think the line is pretty clear there. Like, either you can fall in traps or you can't fall in traps. You can fall in traps, then you have to be careful and you need someone else's help. Parents, whatnot, some nice environment, some engineers help you. And there is no way around that. I think you can just see it with this little tabular MVPs that if you have an algorithm that goes in and has no idea about whether there are traps in the environment or not, either it misses a big reward, which is pretty shameful, or it's going to fall sometimes into traps.
So I agree about the eternal hell trap. I think it's impossible to do anything about. But what about just large negative rewards being hidden in the maze? If you're just learning, if as you go you learn it, you're noticing the more you explore, the more negative your total reward is getting, and that's not turning around, then you might have some meta process that's saying, hey, exploration is not really helping me in this MVP.
So just pure, the naive way of doing optimism in terms of say optimistic initialization would maybe not be able to figure out that this negative reward is hurting you in some way. But if the negative rewards are highly negative, confidence-based methods or uncertainty estimation-based methods may be useful in this regard. But I haven't seen a scenario where they've been deployed. If I were to take an optimism in the face of uncertainty method and a naive exploration method like epsilon greedy in a really simple MDP where we don't need exploration, then optimism in the face of uncertainty method would definitely mostly do worse than the naive exploration method. So its goals are a little misaligned with respect to an easy MDP.
So can functional approximation in fact help in this case? I was just writing it, but then I'm just speaking, because imagine that you've experienced some states and you've gotten really negative reward, and then your function approximator tells you that this new state is similar to that you've seen. Maybe it can actually help you not explore it in this safe exploration setting.
Yeah, I think that's definitely promising. And if you had a good function approximator or a good representation, which alias tastes well such that you learn from one state, you can definitely generalize to the other bad states. That sounds super ideal, but it's not accounted for in the optimism. In the case of uncertainty setting, it's kind of accounted for in the representation learning setting, hopefully. Not problematic.
Yeah. And regarding Prabha's comment about the traps, I think the setting she mentioned was like episodic, right? So like the resets would get you out of any trap you fall in, right?
Yes, like here in the episodic setting, you would have the reset to hopefully overcome the past bad experience you had. But if you're considering healthcare, it's not
Yeah, but if it's like continuing, then you might need a way to get out of it. Like otherwise you'll just be stuck there, like real life, I guess. I don't know.
so games have been promising in that regard.
So Bayesian implies priors, right? Did we talk about the priors?
No, I kind of just skipped over them by mentioning that there's a prior that exists, and I think Kuram just commented similarly with that. The assumption behind these priors is that they are general and comprehensive enough to include the real scenario, so the real MDP we would be interacting with.
Raksha, I have a very big question about this Bayesian method. So you think that the Bayesian methods, so it's really essential to be Bayesian, or is it like that you should induce some principal randomness, like this stochastic dominance or whatnot, like in some way, and Bayesian methods are one way of doing that, but there could be other ways? Like how important it is that you actually calculate a posterior and actually do something with a posterior? Or is that just one tool that arrives at the desired result?
I think it's one tool. Like if there are alternatives which are, let's say, more tractable, computational. Sorry?
Bootstrapping.
Yeah, but bootstrapping-based methods and uncertainty estimation has been kind of a little open-ended.
Okay.
Right. So there are bootstrapping uncertainty estimates for bootstrap-based methods, but they're optimistic with respect to the bootstrap signal, which itself might be wrong. So that's one limitation.
Let me give you a reference. There is a very nice new bootstrapping paper that I really like because it corrects for these problems. It may be inspiring to try to put this into RL.
That sounds interesting. Really good. But yeah, I don't think it's necessary to be Bayesian if we could learn other forms of reliable uncertainty estimates.
But I guess I hijacked Robin's question. His question was really about the prior. So where do you get, like, if you want to be Bayesian, where do you get your prior? I think that's the question.
Even in RLSVI, where they show effective tabular regret, it's all conditioned on the prior having a particular structure.
Mm-hmm.
But when it comes to actual empirical experiments, I think knowledge of maybe the capacity of the function approximator or some notion of how your function approximator is generalizing over the space would be useful for defining useful priors. but I haven't really worked
You
with these.
mentioned a prior over MDPs somewhere. What would you do in that case? Like, how do you know that, like, at all? So do you start off with a uniform prior, or like, what do you even do?
You start off with a uniform prior that is broad. So it's not just that the uniform prior sounds bad, but if your space is large enough, then a uniform prior has at least all the feasible sets. So although computationally intensive, because you have support, this method would converge towards something reliable. But in the function approximation case, it's kind of hard to just say that, I think. But I haven't really worked with them in function approximation a lot. My experiments have been limited to RLSVI, which honestly was a little hard to tune in the linear function approximation setting. Which, I don't know if Matt is still here, but he had tuned quite a bit and felt the pain too.
All right, if there are no more questions, we can...
I have one more question, if you don't mind.
Yeah, go for it.
So you said, I understand the optimistic value function, but you had a line that said, mentioned optimistic model. And that's not clear to me. What does that mean, optimistic model? What is it optimistic in? What sense?
So let's say the very abstract prior over MDPs is over the possible transition and reward dynamics with respect to MDPs. That gives you a posterior over the possible transition and reward dynamics, which were in the prior set. So what do I mean by optimistic model estimates? You're going to combine these posterior estimates over transition dynamics and the posterior estimates over reward dynamics to give you MDPs, which are feasible. So in that set of MDPs, which MDP would be the most optimistic MDP in the sense of which MDP would give you the most reward would be an estimate with respect to optimistic model.
Thank you.
Parting comments. All right, let's all thank Raksha for the talk.
Thank you.
Thank you. Nice talk to you.